Welcome to this eLearn Security video training lesson on iOS application reverse engineering. In this video, we will see how to use reverse engineering techniques and tools that may help us to discover hard-coded information in the application binary. It will also help us to understand the logic flow of the application and bypass any security checks implemented in the app itself. The first step when we start to reverse engineer an iOS application is to gather as much information as we can about the application. To do this, we are going to use a few different tools to help retrieve information about methods, objects, classes, and other valuable information stored in the binary of the app. In the first part of the video, our target application will be Gmail for iPhone. The extension of iOS application is .ipa. It is a simple archive that contains all the necessary files and folders for the application to work, such as the ARM binary, icons, images, and scripts. Usually these files are encrypted, but for this video we are going to use a decrypted version of the application. Once we have the .ipa file, we need to extract its content in order to retrieve the binary. To do it, we simply change the extension from .ipa to .zip. This allows us to change the file as any archive and then display its contents. Each application always has the same files and folder structure. In the root folder, we can find files such as iTunes Artwork, iTunes Metadata.plist, and a folder named Payload. The file iTunes Artwork is the icon displayed in the device springboard. The file iTunes Metadata.plist contains information about the app, such as the developer ID, the name of the app, and its version. On any device with Mac OS, we can simply double-click to open this file and read its contents. As we can see here, this is where the file contains the information about the app and its developer. The Payload folder is the most interesting folder in this archive. Within this folder is the actual app that is stored as a package with the .app extension. We can inspect this file by right-clicking on it and selecting Show Package Content. In this app package file, we can find all the files that the application needs to function. For example, we have folders for different languages, images and icons used by the app, and audio. The two most important files contained in this folder are the info.plist file and the binary of the application, which usually has the same name as the app but has no extension. The info.plist file contains information about the app, but it may also contain information added by the developers. It is a good practice to look into this file since it may store valuable information. The other file is the application binary, and this will be the target for our reverse engineering tests. Since it has been compiled to run on iOS devices, we can't execute it on this machine nor on the simulator, but we can use a few tools to get information about the file. One of the first tools we are going to use is called OTool. OTool allows us to gather specific information from these binaries, such as the headers, sections of the binary, and even disassemble the file. Let's start a new terminal and run the command OTool without any options to display the help contents. As we can see, the tool has many options that we can use, and each of them has a specific purpose. For example, let's start from the first one, the -F. Let's move into the application directory at the same level of the binary, and then run the command OTool -F Gmail hybrid. This command returns information about the FAT headers. You should know that when an application is compiled to support different architectures, the binary is fattened with native code for different processor types. As we can see in the results of the command, the application has been created to run on two different architectures, ARMv6 and ARMv7. The command also displays specific information for each of the listed architectures. For example, we can see the magic number used by the OS to recognize the binary that is going to run. The CPU type value is the number that identifies the type of the CPU. Here the number 12 means that the CPU type is ARM. CPU subtype identifies the subtype of the CPU. In the first case, 6 means that it has been compiled for version 6, while in the second case, 9 identifies that it has been compiled for version 7. So basically the first architecture identifies the binary for ARMv6, while the second identifies the binary for ARMv7. We can also see the offset and the size of the code for both architectures. As we will see in the runtime analysis part of the video, these values will come in handy to calculate the portion of memory that we have to dump in order to get the decrypted versions of the application. By adding the V option to the previous command, we can obtain the same information, but this time the number will be replaced with something much easier to read. Now we can see the meaning of each value. Another command that may be useful to get information about the binary headers is the option --h. Let's use the V option again to print disassembled operands symbolically. With this command, we get the information from the mock header. The results of the command are very similar to the results of the previous command, but we now have additional information such as file types and flags. File type indicates the usage and the alignment of the file. In this case, execute is the format used by the standard executable programs, and flags contains optional features of the mock-o file format. We can also instruct OTool to print information from a specific architecture by adding the option -arch, followed by the architecture we want. For example, let's set ARMv7. As we can see, now only the information regarding ARMv7 architecture is displayed. We can use the option -L to print all the shared libraries used in the binary for the ARMv7 architecture. One of the most important options that the tool offers is the -O option, which prints the Objective-C segment. Let's use this option and see what we get. As we can see, since the app is big, we have a very long output. The information contained in the output is very useful to understand the application itself, since the information may be useful to understand which classes and methods prototypes are implemented. In order to understand the output of this command better, let's use a smaller application. Let's use our application named iOS ELS Foo App. Since we have the source code of the app, it will be much easier to understand the information printed by the command. So let's move into our iOS ELS Foo App package and run the previous command against the new binary. As expected, the output is smaller. Let's go to the beginning of the output and start digging into it. Here we can see that the tool starts printing information of classes for which there is an implementation in the binary. As we can see at the following line, the first class is the class named AppDelegate. And right after the name, we can see a list that contains all the methods implemented and some other information. To understand better what this information represents, let's open the source code of the app and see if we recognize any of the listings. Once the project loads, we can see on the left pane a header and an implementation file named AppDelegate. If we open the implementation file, we see the list of methods implemented, and these are exactly the same methods printed by OTool. And as we can see, they are the same listed in the output of the previous command. Right after the list of methods, we can see other information. This is information related to the app-delegate header file. If we open the app-delegate.h file, we can see the interface implementation as well as the properties defined in it. The --o command may be very useful to get information about the application structure, but as we will see in a few minutes, there's another tool that prints out this information in a more readable format. Before moving on, let's run OTool again with a different option. This time we want to use the option --TV option, which will disassemble the application. As we can see in the output, we have disassembled code of the entire application, and we can see the bytecode of each method. As we can see, the output is not very good, and it's worth noting there are other tools such as IDA or Hopper that can do better. But it may still be useful to get the disassembled code of the app very fast. We won't spend too much time on the OTool output since we are going to see the decompiled app in IDA. Let's first use another command line tool called class_dump_z. This tool is an Objective-C interface extractor written especially for iOS binaries. If we run it without any options specified, we get the help manual. There are many options that can be used to get specific information output. But for now, let's try to run the tool against the binary without any of these options. Here we get information about the application structure. All the information is organized similarly to the header file and the implementation file in the source code. We can see information for each class in the binary, as well as its methods, interfaces, properties, and instance variables. Here we can see the interface view controller, the property set in its header, as well as the implemented methods. This output may be very useful to understand which methods to target for our tests. For example, we will focus our tests on the method access, since it's the method that verifies if the code inserted by the user is correct. So to review, if we don't have the source code, the information obtained with these tools may result in very useful information for our testing purposes, especially when we run runtime analysis against the app. Now that we know how to get some of the information contained in the binary, let's focus on how to disassemble the binary. For this part, we'll use one of the best tools available for disassembling iOS applications, IDA Pro. Let's run it and load the app binary. As we can see, IDA recognized that the binary has been compiled for ARMv7 architecture and asks if we want to continue. In addition, it identifies Objective-C structures and asks if we want to parse them and rename the methods. Let's select yes and continue. Once all the operations are completed, we can see that the app has been successfully decompiled, and we can start our investigation. In the left panel of IDA, we have the list of methods stored in the file. Here we have the main function, followed by all the methods that we have seen previously with the other two tools. IDA also tells us the segment for each method and some other information such as the offset and its length. The most interesting pane is in the main window on the right. Here, IDA displays the disassembled code of the app. As we can see, the IDA output is much better as compared to what we saw in the OTool output. We can select any of the text in this view and perform specific functions by right-clicking or double-clicking on them. Also note that if we double-click on any function on the left pane in the main pane, we will immediately jump to its code. Here, for example, if we double-click on the access method, it automatically moves our cursor to the first command of this method. For now, let's use a different approach to discover where the code checks if our passcode entered is the same as the passcode stored on the device. Let's try to run the application and see what happens when we insert a wrong passcode. In this case, we are using the simulator, but we could also use the actual device. Of course, we don't know the correct passcode, so let's insert something into the field and click Login. As we can see, if the passcode is not correct, the message "Wrong Password" is displayed on the screen. This is very useful information that will help us to locate the correct portion of code that does this check. So let's go back in IDA and open the subview strings from the top menu, View, Open Subviews, and then Strings. In this view, we can see all the strings identified in the binary. Let's search for the string "Wrong Password" by clicking Search in the top menu. Here's our string. If we double-click on it, IDA will open the main view and will move our cursor to the string definition. Now let's right-click on the string and select Jump to XREF to Operand. This option will open a window showing where the string is used in the code. Here we have two entries. Let's select the first one and click OK to jump into the code. Here we can see a portion of the code that may be used right after a compare. As you can imagine, this is exactly what we were looking for. This is the portion of code that verifies if the user passcode is correct, and if it is not, will print the message "Wrong Password." Otherwise, it will print "Congratulations." We can double check it by opening the graph view by right-clicking on the code and selecting Graph View. As we can see, once the code executes the compares, it may then go in two different portions of the code. The one that will display the message "Congratulations" and the one that will print "Wrong Password." If we go a few lines backward, we can see the string is equal to string. This is where the code compares the password. Now we know that somewhere in the above portion of code, the program may load the correct string to compare. So let's go a few lines back. Here, there's a string ELS1234. This is exactly the string that will be compared with our password. We see the code first loads our password from the text field. Then it loads the hard-coded password, and then performs a compare of the two. So let's go back into the app and let's try to insert the password just discovered. The password is correct. And now the message "Congratulations" is displayed. In this video, we have seen tools such as OTool, ClassDumpZ that are very useful to gather information from iOS application binaries. We have seen how, thanks to these tools, we can easily get the list of implemented methods, instance variables, and properties. Additionally, even if it was a simple application, we have seen how we can disassemble an application binary in order to understand how the application works, or how we can get hard-coded information that may be useful to bypass security checks within the application. Note that the latter may require some reverse engineering skills to succeed, and this was out of the scope of this current course. Thank you for joining us.